Okay, welcome to the review. This is the first time I'm doing this, as I told you. Question number 1 talks about an object accelerated from rest. So the initial velocity is 0. The final is 20 meter per second and the time is given. What is its acceleration? Definitely, acceleration is v final minus v initial divided by t, which will give you 1 meter per second squared. And there is no doubt about that one. The second one says if the mass of the object is 2 kilogram, what is the net force required doing that? According to Newton's second law, net force is mass times the acceleration. Therefore, all you got to do is, remember it's net force. The mass is given to you. You got the acceleration right now. Put them together, multiply them, and you get 2 newtons. Question 3. What's the weight of the object? The weight of an object is always m times g. Mass times acceleration due to gravity. And it always acts vertically down. So the mass is 2, 9.8 meter per second squared is the acceleration due to gravity. So you get 19.6 newtons. Number 4, what is the normal reaction? The question seems to say that it's on a flat surface, isn't it? If it is on a flat surface, then the weight and the normal reaction are exactly equal and opposite. Therefore, the normal reaction is mg. But that only happens if it's on a flat surface. Number 5, the surfaces in contact have a coefficient of friction of 0.4. What's the force of friction? Force of friction is mu times Fn, isn't it? So mu times Fn, mu is 0.4 times the normal reaction that you got just now, which is 19.6. So multiply those two, and you will get the force of friction on this object as 7.84 newtons. Now, number 6 says, what is the net force to accelerate it as given in question 1? Now, you have to be careful on that one. I've just introduced friction, right? And again the question comes, what should be the net force? Remember, one time we got the net force as, in question 2, we got it as 2 newtons. Will that answer change? What's the formula for net force? Mass times acceleration. Is the mass changing? No. Did the acceleration change? No. Therefore, the answer does not change. Even if there is friction, net force is still going to be the same. Okay, I think I didn't do that part. Okay, so it's still going to be the same. It's 2 newtons again. The net force is still the same. It's still 2 newtons. Now what I have done in number 6 there is to find the applied force. Is that making a difference? The applied force increases. And the applied force is 9.84 newtons. I'm saying it again. The net force is what you're asked to calculate, isn't it? That will stay at 2 newtons. But definitely the applied force must be greater. Why? Because there's no friction. So you have to apply 9.84. What's the frictional force? Be with me, what's the frictional force? Wasn't it 7.84? So if you apply 9.84 and friction is 7.84, what's the net force? 2 newtons. That's what I'm trying to show you. So the net force is 2, the applied force is 9.84. Number 7, the surface is like that. I've already drawn it. The forces, mg sine theta down the incline, mg cos. That comes from the weight being resolved into 2, like I told you. The acceleration is still 1 meter per second squared, isn't it? Same thing. Number 8, what's the net force required? Net force, what's the formula? You have to think clearly. Net force is mass times acceleration. It doesn't matter whether it's on an incline or whether it's on a flat surface, doesn't matter. So it's mass times acceleration. Did the mass change? No, acceleration didn't change. Net force is still the same. Net force is still going to be the same. And then I wrote it on the other side. Okay, I have to try it again. All right. I included another force now. Which one? The applied force. Because if this object is going up, it can't do that on its own, can it? So it's understood that somebody is pushing it. So now you have all those forces that you see either along the x or the y. Correct? Except which one? Mg. And that's why that's broken up into mg cos and mg sin. Said it a million times. Okay. Net force is still the same. Net force is mass times acceleration, so that's 2. Weight, does the weight change? No, weight is still the same. But don't worry about that. I'll explain that later on. Or maybe you already understand what's happening. Did anybody understand what I did now? What's the net force along the x-axis? Net force along the x. There's Fa acting up. There is mg sine theta acting down. So what's the net force? Fa minus mg sine theta, isn't it? I've not introduced friction yet, have I? No. So there's no friction right now. That's why I wrote Fa minus mg sine theta is equal to 2. Where did I get the 2 from? Because the net force is 2. Didn't we already calculate the net force as 2? But from the figure, the net force is Fa minus mg sine theta. So I'm trying to find Fa. It's mg sine theta plus 2. And that gives me 8.7 newtons. That is the applied force. Now what's the net force? 2. Applied force is different from the net force. Alright, now find the, okay. Number 10, the normal force is mg cos theta. The normal force is mg cos theta, which is 18.42 newtons. 18.42. Friction is mu times Fn, which is 0.4 times 18.42, which is 7.37. That's the friction. The next question says, what is the net force to accelerated as given in question 1? How many times have I spoken about that? What's the net force? 2. Net force is 2. I think I messed up on that question number. I did not write that. That's actually 13. Because 13 says how far up the incline does the object move in 20 seconds, isn't it? Okay, let's go. What's the initial velocity? 0. So you know that. Do you know the time? Yes, it's given us 20 seconds. Do you know the acceleration? 1 meter per second squared. And you're asked to find delta x. What equation comes to your mind? The king. The king. V naught t plus 1/2 at squared. But didn't you tell me that the initial velocity is 0? If that's the case, this whole term becomes 0. So you only have 1/2 times 1 times t squared. 20 squared is 400. So it would go up 200 meters. It would go 200 meters up the incline. Okay, now I changed it to that should be 14. Potential energy is mgh, which is mgd sine theta because of what I did here. Isn't that clear from here? H is d sine theta. So 2 times 9.8 times 400 times sine 20 gives 2681.44 joules. Did any of you get that? Yes.
Where'd you get
Oh yeah, I made that mistake. It should be 200. I think I corrected it later on, or maybe I did not. Please change that to 200. It's 200, not 400, 200. So what's the actual answer? I think I changed it. We'll see. Okay, half of that anyway. So the idea is there. Maybe at the end I changed. 15. What's the formula for kinetic energy? 1/2 mass times velocity squared. All right? Okay, there we go. Kinetic energy. Here. The mass is given. Do you know the velocity? 20 meters per second. So it gives you 400 joules. How do you find power? Power is work over time. But didn't you do 3 types of work? And I know you should not be copying without understanding. Look at this. At the bottom, what was the potential energy? At the bottom of the inclined plane, what was the potential energy? 0. What was the kinetic energy? 0. Now, by the time it reached the top, it has potential energy, it has kinetic energy, and also you did a lot of work against friction to get it up there. So, to get the total work, you will have to add all the 3. Which 3? The potential, the kinetic, and the work done against friction, because all that came from you. If it was you pushing, isn't it? That's what I've done. So you can see that I've added all the 3. That was the... Yeah, that has to change, because you see, it's half of this, right? Change it to what? 13?
1340, right?
Okay. Plus 400 plus this, divided by 20. Somebody give me the right number.
It's 106.7.
It is. So I only had to change, because I was finding the answers while they were working in class. That's why. So I've corrected those numbers, and here 18. Omega is 2 pi times f. F is the rotations per second, or the linear frequency. Omega is the angular frequency, and you get 31.4 radians per second. That is the unit of omega.
Is that omega or W?
Omega. Okay, so again, when you rearrange, you're going to get the linear velocity as the product of angular and radius. The angular velocity is 31.4. The radius is 50 centimeters. Did anybody notice that? It's in centimeters. Okay, you have to change it into meters. That's why you get a 0.5. 50 divided by 100.5, multiply the 2, you get 15.7 meter per second. All right, directly on to 20. Does anybody know the formula for centripetal acceleration? What? V squared over r, yeah. V squared over r. So centripetal acceleration is V squared over r. You just got the linear speed, and then when you plug it in, it's going to be 15.7 squared divided by 0.5. Check that out, please. Do you get 493?
15.7 squared divided by what?
Divided by the radius, which is 0.5. Once you're given the centripetal acceleration, if you cannot find the centripetal force, oh my goodness. You have the acceleration, how do you find the force? Multiply with the mass, right? Okay, so centripetal force is mass times the acceleration. That is going to be 0.1 times 493. Because we already got the acceleration, didn't we? We need not start all over again. 0.1 times 493, which is 49.3 newtons. So we have to know what we are talking about. We have to know that the centripetal force in this case is the tension. See, that's what I've written. The tension is nothing but the centripetal force. Therefore, it's 49.3 newtons. And the next one says, what if the maximum tension that the string can withstand is 50? What's the maximum number of rotations that can be made per second? Please add per second. What is the maximum number of rotations that can be made in 1 second without breaking the string? Okay, 223. Tension is m omega squared r, like I explained just now. Therefore, when I make omega the subject, I'm going to get square root of ft by mass times radius. The tension is 50, the mass is 0.1, the radius is 0.5. Calculate carefully, you'll get it as 31.62 radians per second. That's omega, isn't it? And then you'll have to go put it back into 2 pi times the frequency and get the frequency. And that will be omega by 2 pi, just a little bit more than 5. (24) What's the weight? Weight is mg. It's the same thing. 100 times 9.8, you get 980 newtons. 25. What is the gravitational force? G, mass of the object times mass of the earth by square of the radius of the earth. Okay. That's the universal gravitational constant. Mass of the object is 100. Mass of the earth divided by the radius converted into meters. And do not forget the square. You get 9.67 times 10 to the 2 newtons. All you have to do is apply the same thing, but remember that the distance increased by 10 kilometers. Therefore, same thing. Nothing except the distance changed. And you will see now that the distance has become 6.39 times 10 to the 6. That's because 6380 plus 10 is 6390. That's changed into meters, and you get the answer as 9.63963. Didn't you expect it to decrease? Because don't you know that as you go up, the acceleration due to gravity decreases, right? So it should weigh a little bit less. It did, sure enough. Lost 4 newtons. Don't, maybe. Okay. Flip. It's not done. 28. 28. Look. 28 comes from here. What are you looking for? Which one? What is the linear velocity? Do you know the mass? Do you know the radius? Yes? You know the radius of orbit. You know these two numbers. You're looking for this. Isn't that easy? Rearrange, plug it in, calculate. 28. Okay, and 28, you already know, mv squared by r is 963, and when you rearrange and calculate, you get velocity as the square root of 963 times 6.39 times 10 to the 6 by 100, and that gives you 7.84 times 10 to the 3 meter per second. And this is where we talked about satellites, and I'm sure somebody remembers that to make a circular orbit close to the surface of the Earth, it should be 7.9 kilometer per second. Does anybody remember that? This is a little bit less. Why? Because it's at a height of how much? 10 kilometers. Yeah, that's why. So the higher you go, the smaller the velocity becomes. 29. Time period is 2 pi r by the velocity. 2 pi times the radius, which is that, divided by the velocity that we got just now. But see, when you put a time in seconds, you have no idea of how much that is. Be honest. Do you have an idea of how much that is? No. So it'll be okay, you get full grade for that, but it'll be nice if you change it into minutes. And to change it into minutes, you divide by 60. Now you have an idea of, well, that's about 1 hour and 30 minutes. Isn't it? It's 1 hour and 30 minutes to go around the orbit. We're talking about something going around the Earth. I don't know whether you're getting what we're talking about, okay? Only takes 85.3 minutes. Isn't that what you said, Nicholas? That's all it needs? There we go. 30 is the same because it does not depend on the mass. 31. If the speed of the object is slightly increased, what change would occur? What change will happen? Right now, what kind of orbit is it? Circular? What will happen? Exactly. It will become slightly elliptical. Just a little bit. But if you keep on increasing it, you do know that when it reaches 11.2 kilometers per second, it just escapes, okay? So that's what you have to know. Okay, here we go. 32. Potential energy is mgh. Therefore, you only look at the height. And the height is... Wait. What is that? What are we doing? I don't know. So it's 19,600 joules. What is its kinetic energy at the point when it's just projected? Wait, tell me, what's the formula for kinetic energy? Mass times velocity squared. Do you care about the angle? No? What's the velocity? 30 meters per second. So all you have to do is just go kinetic energy is 1/2 times mass times the square of the velocity. And I got 9,000 joules. Are you getting 9,000? I didn't plug it in because 20 by 2 is 10. And 30 squared is 900. So 900 times 10, 9,000. Are you getting 9,000? Yes, 9,000 joules. All right, 34. We're moving along. 34. What is its total mechanical energy? What do you mean by mechanical energy? Mechanical energy means the sum of the potential and the kinetic. And the word total is there. It's the sum of both. Add them up. So total mechanical energy is the sum of potential and kinetic. Add them up and you get the answer as 28,600 joules when you add them. What is its potential energy just before hitting the ground? Just before. What's the height? The height is 0, isn't it? So the potential energy is 0. That's it. Because the height is 0. 36. Now that's a good one. What is its total energy just before hitting the ground? Who can give me the answer? What do we know about the total energy? Conservation of energy. Total energy has to be a constant, will be the same. So the answer is 28,600 joules. Total energy never changes. Therefore, total energy is 28,600. Hold on a minute. But didn't we say that the potential energy is 0? Doesn't matter. Now look at the next question. 37 says, what is its kinetic energy just before hitting the ground? Who can give me the answer? 28,600. Because didn't we already say that the potential energy is 0? But yet the total should be 28,600. So what does that mean? All of it is kinetic. Come on now. Because the total energy means potential plus kinetic, isn't it? Potential is 0 because the height is 0. Therefore, whatever is the total should be the kinetic. Okay, so the kinetic energy is 28,600 joules. Get 53.48 meter per second for the velocity. Recording now. 39 work. Force of friction times distance. 1 times 150. I don't know why I put the units now. Anyway, 150 joules. Number 40. This was the kinetic energy if there was no air resistance. So that much is lost. So take away that number and you get 28,450 joules. 41. Calculate the velocity in this case. What do you do now? How do you calculate the velocity? Once again,
Put it back in.
yeah, put it back into 1.5 times mass times velocity squared and do it. Do you expect the velocity to be a little bit smaller than in the last case? Yes. So you get 53.34. Oh, I'm sorry. 53.34. What was the answer in the last case? 53 point.
48.
See? You see that it's just a small amount. That's why we do not usually consider air resistance. You see? For that small difference. But you had to know that there is going to be. In the friction lab, the setup was something like this. You had the block moving over the table with the string attached, passing over the pulley, and another mass suspended there. This was little m, this is caps. And when you try to draw the free body diagram, you look at the forces acting on each one individually. Okay, so let's look at the forces acting on this mass. There are only two forces acting on it. One is its weight down, mg, and the other is the tension in the string acting up. And because this is, okay, tension has to be less than mg, because this is moving down, the force acting down on it must be greater than this. So what's the net force? Net force is mg minus ft. Now on the second object, the forces acting are, on this one, its weight acting down and the normal reaction. You also have the tension acting along the string and friction in the opposite direction. Okay, this is the application of Newton's law to the bigger object. Looking at the forces along the x-axis, there are two forces. One is Ft, which is greater than friction. Why? Because it's moving this way. What's the net force? It's Ft minus friction. But we do know that friction is mu times Fn. And in this case, Fn is equal to mg. So I put it all in one step. Ft minus friction. But friction is mu mg, and that should be equal to mass times acceleration. Alright, for this hanging object, this force is greater than Ft because it's going down. So mg minus Ft is equal to its mass times acceleration. Add the two equations, the Ft's cancel out. On the right hand side, A is common between the two, so that's taken out. Rearrange. Divide both sides by mg and you get the equation for coefficient of friction. So I've answered all questions from 42 to 45, maybe 43 to 45. Okay, so use this to prepare for the exam. Thank you and good luck.